Thank you for this opportunity to share some mathematical ideas with you using technology. You've all had 2 concentrated days of problem solving, so you deserve a break. In this presentation you'll be seeing examples of applications in sport, the Navy, complex numbers, the world of CGI in the movies, runway numbers, and the use of a parabola and its focus. So I have a rough idea who you are, but I don't know where you are, except I assume you're mostly in India, but also in some other countries in this region. But you probably don't know where I am, so let's have a look. I'm at a place called Oundle, which is north of London and sort of northwest of Cambridge. So we're going to have a look now at some mathematical objects that you can see by using the wonderful Google Earth. So let's go to Australia and double click on the N to make it in the right place. And what we're going to do is zoom in on that little pinprick out here using the scroll on the mouse if you've got one. And you very quickly find yourself in the company of the world's largest hexagon. How large? Well, get the ruler out and measure it. It's 1.2 kilometers, which makes it a pretty big hexagon. It was built in the Second World War to communicate with submarines in the Indian Ocean. Submarines need a very low frequency in order to receive a signal under the water. And that's what that was for, and it's still there. Well, there's not a lot left of it, I have to say. So we'll now go and find the world's largest pentagon, which of course is the pentagon that we know in Washington, Pentagon Building, Washington. There it goes. Search, is it going to go east or is it going to go west? East. And there's the world's biggest pentagon. Obviously a big opportunity. I'm a great fan of using real objects rather than drawn ones, so if you're investigating the interior angle of a pentagon, then stick that up on the board, get a protractor out and measure it. Now, what have we got down here? We've got an airport, which is Washington National Airport, which has runway numbers at the end of each runway, as every runway on this Earth does. What do they mean? Well, they actually mean the angle to magnetic north in tens of degrees. So that's 150 degrees from magnetic north. This is 190, which doesn't look quite right, does it? Because magnetic north isn't always the same as true north. And in fact, in the case of Washington, D.C., it's about 16 degrees out. Just move that over there, that's more like it, and that now is 100. So you could ask questions like, what's the number on the other end of this runway? That's a good mental exercise. Preferably without cheating, of course. I'm sure you all got 33. You can see that Google Earth now goes underneath the waves as well as on top, so you can see the continental shelf. It's very easy to get north out of kilter. Now, there's a very interesting parabola down here that you need to see, which is just by this bit sticking out here called Dungeness. There's 2 power stations there, and there's another runway here. What would that be, about 03, do you think? Yes, perfect. Now you just go to the junction here and go further across here, and you should find yourself in the company of the world's biggest parabola. There it goes. And that is indeed a parabola. It was built again in the Second World War, pre-radar, to try and hear planes before you could see them. So here it is, and we'll now take it off into autograph and see what we've got. First of all, we want equal aspect. I think we have, yes, that's good. I've plotted x equals ky squared, which is this way around, and we'll use the constant controller. Now, is k going to be bigger or smaller to bring this down this way? But first of all, we need to locate the parabola exactly at the vertex. There it goes. And k is going to be less than 1, of course, to bring it down. But we want a 0.1 will do. And then reduce the step, and up we come. So it is a very good fit. It clearly was a parabola, but one might ask the question why. Why was it not a circle or an ellipse? So we'll put a point on here, and right-click, do a horizontal line, and right-click, do a normal, and then we'll take a point on this line, and select it and this line, and right-click, transform it by reflection. So now if we select this and right click, line, straight line. Now what happens if we move this point around? Something quite interesting is going on down here. So get the pen, and there we are. And that is the focus of this parabola, because all parallel rays that hit the parabola end up going through the same point, which is why that's where you have the listening device if you're going to make this into a parabolic mirror. And that, of course, is why there are so many parabolic shapes around the place: mirrors, headlights, satellite aerials, and all sorts of things. So now I've got some classroom applications that might be of interest to you. First of all, we'll have a look at Fibonacci. The sequence that's named after this Italian mathematician is all-pervasive, so let's have a look. First of all, piano keys. Who would have thought that piano keys have anything to do with Fibonacci? But they do. How many black notes are there here? 2. How many here? 3. How many in all? 5. How many notes in the C major scale? 8. How many notes in the chromatic scale? 13. Boy, where have we heard those numbers before? Let's have a look at this in a spreadsheet. Okay, so to generate the Fibonacci sequence, it's 1 and 1, and then this one is equal to the 2 before it. So that one plus this one. So that's going to be 2, of course. 2 and 1 makes 3, and 3 and 2 makes 5, and those are the numbers that we've just come across. We double click on that dot, or drag it down, that'll do the same thing. There we go. Here's 2, 3, 5, 8, 13, as we have in our piano keyboard. Now to get the golden ratio, you just have to do equals that divided by that. That's 1, double click on that, 2, 1.5. Look at this, it settles down at a particular value very quickly. We might want to take these a little bit further just to get it really settled down. 1.618034, yes. Turns out to be very robust, this. You can change that one to 23 and it still works, or you can change the other one to minus 34 and again it still works. We're still getting the same values here, the golden ratio. So I had an experiment in a school I visited recently. I got all the students and the staff and everybody to measure their height and measure the height of their belly button. And some extraordinary results, really. This is the ratio of that divided by that, and the average of this lot turned out to be 1.664. Well, 1.618 is the golden ratio. So quite bizarrely, the same ratio as the number of black keys on a piano is the height of your belly button in the human body. Quite extraordinary. Now let's have a look at some mathematics in 3 dimensions. After all, every time you go to the movies, the chances are that about half the movies you see are drawn by a computer rather than with actors. Now this is pretty old now, but the principle is the same. In 2 dimensions, if you want to recreate any sort of curve, it's just a series of very short line segments. Now in 3D, it's a series of very small triangles. That's the only way you're going to get a surface. So let's see if we can replicate this. Here I've got some points that I hope to create a small spacecraft. So here we go. I'm going to do it with 2 triangles. As I said, triangles are the way forward. So select, and right click, group to shape. Perfect. Around the other side, select, and right click, group to shape. Okay, now most school curriculum teach about transformations in 2 dimensions, but very few go on to 3, and yet we live in 3 dimensions all the time. It's exactly the same principles. So select that, and right click, transform, enlargement. Let's do an enlargement of scale factor 2. So it's going to double all the distances, so it's going to produce a shape up here. Yep. These are still selected, so I'm going to hide those. I'm going to select this one, and I notice, not that, I notice that the animate object is lit up, so I can animate this. 2 down to 1.9 and so on. So if we take it back to the beginning, then it's time for a bit of action. Let's have lights and action. So there you go. It's just very simple school level mathematics imitating what's done obviously at a much more sophisticated level in the cinema. Now the next exercise is one of vectors using battleships. It's every commander's dread of bumping into another ship. So it's very important that they know what their course is and how it relates to any other vehicles that are nearby. So to illustrate this, I've got an autograph file and I've got ship A that's going with a speed of 1 to the right and 1 down, and ship B which is going to a speed of 1.5 to 2. Now distance is speed times time, so all we've got to do is multiply the elements of this vector by t and we will get something which then represents displacement. So double click on that. I'm just going to put a t after each expression. Same with this one, double click, t and t. What that means is that the constant controller now can control the passage of the ships. Aha. Alright, so how close are they? Well, one way of doing it is to put a line segment from here to here. And you see I've got a point down here, so if I now choose this segment and this point, I can draw a circle. So right click, circle, center and radius. Perfect. Now we just vary t. And when do you think the circle is at its closest? Round about there. So that's one way, slightly less sophisticated way of doing it. The other way to do it is to do vectors. And if I select this vector and right click, vector, negative vector, I'm putting a negative vector which effectively reduces ship B to rest. So ship B is not moving anywhere, and if we put this vector also on this one, in other words we copy it over, vector copy, this ship has two vectors acting on it, and it's one there, and I put the answer here, and we can add them together, vector add. So as far as an observer on B is concerned, ship A is steaming down here. So let's have a look and see if it is. Yes, it is. Perfect. So all we've got to do to find the minimum, the closest distance, is when this is perpendicular to that. To right click, line, perpendicular line. So that is the moment, the exact moment when they are closest. You can of course change the step, or you can zoom in. The next exercise is about complex numbers. You've probably spent a lot of time solving quadratics already, and generally speaking they've got two roots. Now we've got a quadratic equation here of x squared minus 2x plus c, and there it goes. Two real roots, not a problem at all. So we look at the constant controller now, and let's make c smaller than 0.4. It simply gives you more and more real roots. Okay, let's go the other way. And obviously there come a point like here where there's just one root repeated. But then what happens? Now normally you just have to say sorry, no solutions, off you go. But wouldn't it be nice if we could have a look at this in 3 dimensions? Now in 3 dimensions something rather special happens here. We've got x along here and we've got y up here. But up here we have the z-axis, the imaginary axis. This is acknowledging the fact that the square root of -1 exists, and we give it the letter I. So let's explore this and see what happens. Constant controller again. Let's make c bigger, and as it goes up and up you will eventually have just one real root. Then you get 2 complex conjugate roots, and you can look at it from underneath as well. And finally, the problem of what angle to throw the cricket ball at if you're right at the boundary and you want to get it as far as you possibly can. So let's see if we can model this, and here we have a parametric equation representing the cricket ball being thrown at a velocity of v and an angle of 35 degrees, which is the letter B. So what can we vary using the constant controller? Well, B is 35, we can make B more than 35, and will the ball go further? So will it go any further? Let's see. Yes, it's still going, and that's about going to top out around about 43, bearing in mind that 45 is going to be the maximum at the same level as the thrower, but the ball, as it hits the ground, is slightly less than that. So it looks like the maximum along the ground is about 40. So next we have a look at some research that was done at Brunel University. which links the projection angle from your arm against the projection speed, and you'll see that the smaller the angle, the greater the speed. Now, of course, when you've got baseball, the Americans play baseball all the time, and they throw the ball almost horizontally because that gives them maximum speed. Cricket, the requirement's a bit different because we want the maximum distance. That's obtained with a slightly larger angle than 0, and the relationship between the angle and the velocity is given by this curve along here. So, we can fit a quadratic to that, which is a fairly horrible expression here, but let's just use that. So here we have the cricket ball, and you can see that I've replaced the expression for velocity with this expression here from the Brunel research. So at 37 degrees, let's see what happens now if we try to vary b, the angle. Now b is 37. We can vary that. Let's make the step 1, and we make it 38, 39, and obviously even at 40, 50, it's still decreasing all the time. Let's go back and see when we think it tops out. That's about there. Now 31 is in fact a very well known result for anybody who throws things in sports like the javelin or the shot put. It's well known that 45, although the classical mechanics suggests that, the classical mechanics assumes that you can throw at the same speed regardless of the angle. The Brunel research has shown that this is not the case. You can even look at it in 3D. So here we have the ball being thrown from the boundary to try and hit the wickets here. Constant controller. What can we vary? Not h. A is the angle. And you can see that as it goes down, it has its maximum around about 31. Yep. Time to mention the TSM Resources site. It's www.tsm-resources.com. And all the data, images, integer lists, math links, entertainment, general links, a lot of these have been mentioned in this talk today, and there's plenty more there if you want to explore. If you'd like to download the free autograph, you can do so from this link on the TSM Resources site. So I hope you've enjoyed this short journey through the world of mathematical computing. It's my belief that computers and the internet can enhance understanding significantly. As I said at the beginning, in this presentation you've seen examples of applications in sport, the Navy, complex numbers, the world of CGI in the movies, air transport, and the use of the parabola and its focus. So can technology enliven mathematics? Emphatically, yes.